Well, see this next concentration term, mole fraction. See, fraction is common, only mole here attached. So in the previous case, mass fraction is there. So now there is mole fraction. So fraction of moles in the mixture, right? So for this we have a standard symbol X, right? So suppose that we are having this A plus B solution, because until or unless any mixture is not solution, you cannot calculate any concentration term. For calculation of concentration terms, the mixture must be homogeneous. Otherwise, this calculation term or concentration terms are not applicable. So, mole fraction of A, you can write mole fraction of A, XA, is equal to moles of A divided by moles of A plus moles of B. Or you can write Na by N total, right? So this is the mole fraction of A. Similarly, you can write mole fraction of B, XB is equal to moles of B by moles of A plus moles of B is equal to, you can write moles of B by total moles, right? So this is the mole fraction of B. Similarly, now you can write the ratio of mole fraction of A and B. So XB by XA is equal to, you can write NB by NA. Means the ratio of mole fraction in any binary mixture is always equal to the ratio of respective moles, right? And one more thing, that if you okay, one more formula you can write, that XA plus XB is always equal to 1. Or you can write sigma xi is equal to 1, right? Sigma xi is equal to 1 always. right? Because in mixture there is no chance of that moles will decrease or moles will increase after the reaction, I mean after the mixing, because this is not a chemical reaction. So one condition should be there, that in this or in any kind of this mixture, no chemical reaction is considering here, right? So no chemical reaction, no chemical reaction. Otherwise, it is difficult for us to find the number of moles and mole fraction, because in chemical reaction, if at any particular time you have the information that this moles are this moles are this moles are this are present, then you can calculate the mole fraction. Similarly, mole percent, you can write mole percent of A is equal to the mole fraction of A into 100. Mole fraction of A into 100. Similarly, mole percent of B is equal to mole fraction of B into 100. Into 100. So these are the different formulas. You can use this in the calculation of I mean quantity in different homogeneous mixtures, right? Suppose that a question is given that mixture of a homogeneous mixture contains 18 gram of water, 2 moles of ethyl alcohol, and and 12 into 10 power 23 molecules of acetic acid, CH3COH. Find the mole fraction of each component. Find the mole fraction of each component, right? See how to proceed this question. The question is asked about the mole fraction, so each component must be expressed in terms of moles. So you have the moles of ethyl alcohol, but you do not have the moles of acetic acid and moles of water. So first you have to calculate the moles of water. So moles of water, what formula we are going to use? The formula mass of water divided by molar mass of water. So this is equal to 18 gram divided by 18 grams per mole, right? So we will get 1 mole. And moles of ethyl alcohol, it is given moles of C2H5OH, they are 2 moles, it is given. Now moles of acetic acid, CH3COH. So you have formula N by Na. Any number divided by Avogadro's number will give you the number of moles. So the number of moles is equal to 12 into 10 to the power 23 molecules divided by 6 into 10 to the power 23 molecules per mole. You know what is the unit of Avogadro's number? The unit of Avogadro's number is molecules per mole. So molecules cancel, this is cancelled, so this is 2. So this is equal to 2 moles. Now your question can be easily solved. Mole fraction of water is equal to moles of water divided by moles of water plus moles of ethyl alcohol plus moles of acetic acid, right? So moles of water we have calculated 1 divided by 1 plus 2 plus 2. So this is equal to 1 by 5. This is equal to 0.2, right? So this is the moles of mole fraction of water. And what is the mole percent of water? Mole percent of water is equal to mole fraction of water into 100. So this is equal to 0.2 into 100. So this is equal to 20, right? So the mole percent of water 20. Now next, mole fraction of ethyl alcohol C2H5OH is equal to 2 by 1 plus 2 plus 2. This is equal to 2 by 5. So this is equal to 0.4, right? And mole fraction of acetic acid CH3COH is equal to 2 by 5 also. This is equal to 0.4, or you can write this is equal to 1 minus mole fraction of water minus mole fraction of C2H5OH. Either way you can use. So this is the answer. This is the answer of this, and this is the answer of this, right? Mole percent of ethyl alcohol is equal to mole fraction of ethyl alcohol into 100. So this is equal to 0.4 into 100. So this is equal to 40%, right? And here also mole percent of acetic acid is equal to mole fraction of acetic acid into 100. This is equal to 40%. So in this way you can calculate the mole fraction, mole percent, and of other components. Similarly, if you want, you can calculate mass fraction as well from here, right? So what is the relation between mole fraction and mass fraction? Because I mean questions of this solutions and colligative properties, in between you may get mass fraction, and in formula you are required mole fraction. So how to convert mole fraction to mass fraction, or mass fraction to mole fraction? So I am giving you the formula of the conversion of mole fraction to mass fraction. See, mole fraction and mass fraction relation. Mass fraction, how they are related, right? See, you can write the I am taking AB mixture, A plus B mixture, this solution. So mole fraction of B by mole fraction of A is equal to moles of A by moles of B. You can write. Very simple relation. Within second you can derive this relation. Now change this moles of A. What you may write in terms of mass? You can write mass of A by molar mass of A, right? And change this NB. In place of NB you can write mass of B by molar mass of B. So by, so this will come here, right? Now from this equation you can write mole fraction of B, mole fraction of B. Oh, I have written incorrectly. Mole fraction of B by mole fraction of A is equal to NB by NA, right? So here this is B, this is B, this is B, this is A, this is A, right? So XB, you can write XB into MB divided by XA into MA. XA into MA, right? This is equal to WB by WA, right? WB by WA, you can write here. Okay, very simple. Now what you have to do, you have to add +1 on the both sides, and now simplify this equation. So after this addition you can write here XA MA plus XB MB by XAMA, XAMA is equal to WB plus WA by WA. And now see, make the reciprocal of this. So on reciprocal, making reciprocal, what we get? On reciprocating this, we get WA by WA plus WB. What you can write this? This you can write mass fraction of A, right? So mass fraction of A is equal to, you can write XA MA by XA MA plus XB MB, right? So this formula you can use for the mass fraction of relation between mass fraction and mole fraction, right? So now, what is the mass fraction of alcohol or ethyl alcohol or water in the above question? Suppose that another question we have made that find the mass fraction of water in the above question. Right? What is the mass fraction of water in the above question? So you can write here mass fraction of water is equal to, you can write mass of water divided by mass of water plus mass of ethyl alcohol plus mass of acetic acid, right? So now you can write here mole fraction of water into molar mass of water. See here, mass fraction of A is the mole fraction of A into Ma. So mass fraction of water is equal to mole fraction of water into molar mass of water whole divided by mole fraction of water into M of water plus mole fraction of C2H5OH into molar mass of C2H5OH plus mole fraction of acetic acid CH3COH into molar mass of acetic acid, right? So you can write here this is equal to mole fraction of water, I think it is 0.2 into 18 whole divided by 0.2 into 18 plus 0.4 into 46 plus 0.4 into 60, right? So this is equal to 3.6 divided by 3.6 plus 18.4 plus 24, right? So this is equal to 24 plus 18.4 plus 3.6, 46. So 3.6 divided by 46. So 3.6 divided by 46, so 0.078. So this is equal to 0.7, 0.078. So this is the answer. So this is very simple method how to interconvert this mole fraction to mass fraction and mass fraction to mole fraction, right? This is very simple method. Okay, right. Now come to the next concentration term. The next concentration term is molarity. The symbol for molarity is capital M, right? So the next concentration term we have is molarity. Molarity, right? See, first we have to see the definition. After that, we will make the formula. See, molarity can be defined as the moles of solute present per liter of solution, per liter of solution. The important word is here solution. So moles of solute present per liter of the solution expresses the concentration of that solution in terms of molarity, with respect to the provided solute, right? So the moles of solute present per liter of the solution expresses the concentration in terms of molarity with respect to the provided solute. Means if you have more than one solute in any solution, any homogeneous mixture, then you have to express the molarity with respect to each solute independently. Right? So in this way you can express the molarity. Now whatever you have written in English, you can transform this in formula. The same, from here only you can derive the formula, write the formula. Because solute, every concentration term is always expressed in terms of solute. So the molarity is equal to moles of solute, so moles of B, I am taking the same AB, divided by moles of divided by volume of solution in liters. So this is equal to, you can write moles of B by V. So V is in liters. So if you want, you can expand this formula. Mass of B by molar mass of B into V, and if you are interested to write this ml, so V ml by 1000, you can write here 1000. So now this is liter. So this is the, I mean, these are the different formula, different expressions. Basically formula is the same but different in different terms for molarity. And what is the unit for this molarity? The unit is moles per liter. See, moles per liter. See, this is the mole is the, I mean, property of solute, and liter is the property of overall solution. Means liter we are taking here the volume, that is the volume of solution. Means in this case, what we are assuming that this volume, in volume, solute and solvent both are contributing, right? That's why here the word is coming solution. This is not the volume of solvent, right? This is not the volume of solvent. This is the volume of solution, right? So in this way you can calculate the molarity of any solution, right? So how to make the 1 molar solution? I mean, the students have different I mean opinions. Suppose that we want to prepare 1 molar NaOH solution. NaOH solution. So we are I mean going to prepare 1 molar NaOH solution. So for this, what is required? At least you should require 1 liter beaker, right? And see, first you have to expand this as per the definition. So what is the expansion of this? That 1 mole NaOH, and you know 1 mole of NaOH is equal to 40 gram. So you have to take 40 gram of NaOH, and this should be present in 1 liter of solution. 1 liter of solution. So how to make this? How to make this? How to make this, right? So I am giving you the different steps which are used, and this is the method of preparation of 1 molar solution of NaOH in laboratory. Because many of you are lacking in the understanding how to make 1 molar NaOH solution. Some maybe explain you, some I mean teacher or some instructor may explain you that you have to take 1 liter water. Take this 1 liter water and put 40 gram of NaOH here. 40 gram of NaOH, and dissolve this 40 gram NaOH. Dissolve this properly and get the 1 molar NaOH solution. 1 molar NaOH, right? So see, this is not the right way to prepare 1 molar solution, because once you have taken 1 liter of water and putting 40 gram of NaOH in that, you never get 1 molar solution, right? Because you know the whole volume of total mixture is not equal to 1 liter. In this situation, definitely you will get concentration greater than 1 molar. Why? Because when you mix these two in 1 liter, the volume may increase or decrease, because you know this is not the ideal behavior between NaOH and water. So usually we will, practically we get the reduced volume. That's why I am telling you will get molarity greater than 1 molar, right? So what is the correct method to prepare 1 molar solution? The correct method is, first you have to take, let 100 ml water. 100 ml water. Take 100 ml water, put 40 gram of NaOH here, NaOH, and then what you have to do? Mix it properly, stir it, and then after some time, after dissolving this, after mixing this, put more water, put and more water, and make up to 1 liter. So put more water to make up to 1 liter, right? Then only you get the correct 1 molar NaOH. This is 1 liter mark. So by adding more water and putting this up to the 1 liter, so we get the 1 molar solution. So in this case we will get 1 molar NaOH solution. 1 molar NaOH solution, right? So this is the proper way of preparation of any solution, whether it is molar or normal or any other kind, right? So this is molarity. Now come to the next concentration term, that is normality. Normality. The standard symbol for this is N. So this is normality. And how to define? First to write the definition. See, gram equivalents, number of gram equivalents of solute present per liter of solution expresses the concentration of that solution in terms of normality with respect to the provided solute with respect to the provided solute. So the only difference at the place of moles here, gram equivalents. That's it. The only difference is this, right? In place of gram equivalent, moles, we have this gram equivalents. So normality is equal to gram equivalents of B divided by volume of solution in liters. So you can write mass of B by equivalent mass of B into V in liters into 1000, right? So this is the formula for normality. So gram equivalents is equal to weight by equivalent weight. What is the unit for this? The unit of normality is gram equivalents per liter, or simply N, right? Or simply N. Gram equivalents per liter or N. See, what is this equivalent mass? Equivalent mass is equal to molar mass by N factor. So I am not going to much detail of this equivalent mass, because all of you have gone through in already covered this in the class 11th, right? So N factor, equivalent mass is equal to molar mass by N factor. Okay. So this N factor, for example, for acid, the N factor is basicity, right? For basicity means number of replaceable H plus ions, right? For base, this is acidity, means the number of replaceable OH negative ions, right? So for many of acids, number of H plus present there is equal to the basicity. Few exceptions I am writing here, like H3BO3 N factor is equal to 1, although it has 3 hydrogen, right? Similarly, H3PO2, this is N factor is equal to 1, although I have 3 hydrogen. Similarly, H3PO3 have N factor is equal to 2, although have 3. So these are the some exceptions, and rest number of hydrogen is equal to the number of is the N factor. But if reaction is given, so in case of reaction, you have to closely monitor how many hydrogens are replaced there. For example, suppose that we have H3PO4 and no reaction is given. No reaction is given. So no reaction is given. So in this situation, you have to write n factor is equal to 3 because, excuse me, because we are assuming that all these hydrogen which are present, they, excuse me, they replaced in the reaction. But when reaction is given, then you cannot take this n is equal to 3. Suppose that reaction is given H3PO4 plus NaOH. So this is equal to, suppose that NaH2PO4 plus H2O. So see, 3 hydrogens are there, but in the reaction only one hydrogen is replaced. So the n factor for this is equal to 1 in this reaction. So basically, if reaction is not given, then you can take the maximum value, whatever the number of H plus are present there, you can take that. But if reaction is given, then you have to answer according to the reaction. In the given reaction, how many hydrogen are replaced as a H plus, right? So this is the condition. So if you remember these three are exceptional acids. They are exception, except these three, like if H2SO4 is given, H3PO4 is given, HClO4 is given, HCl is given, and in organic acids, the hydrogen which is attached with oxygen, that is considered as a replaceable, not the attached with the carbon. So n factor is equal to 1. Similarly, oxalic acid if given, so the H which is attached with this oxygen, that is replaceable, so n factor is 2. So what you have to do, all of you should remember, these are the exceptional acids, H3BO3, H3PO2, H3PO3, right? So they are exceptional, in which the n factor is not equal to the number of hydrogen atoms present in the molecule, right? So in this way you can calculate the n factor for acid, for base. Similarly, for salt, what is the n factor? The salt for n factor is the number of total positive charge, total positive charge present over cation or total negative charge present over anion, right? For example, suppose that aluminium sulfate is given like this. So how to dissociate this? 2Al3 plus 3SO4 2 minus. So total positive charge. So n factor for this is equal to 2 3 are 6. 2 3 are 6, 3 2 are 6. So in salt, positive charge is always equal to the negative charge. So n factor for this is equal to 6. So in this way you can calculate the n factor. One more type of compound is left, that is oxidant and reductant. But here in this chapter it is not required. So this is normality, right? Now see the next term. So that is molality. That is molality. Molality, and it is represented by small m, right? So see, first you see the definition. What is molality? It is defined as the moles of solute present per kilogram of solution or solvent, per kilogram of solvent. Remember, this is keyword. Solvent expresses the concentration of that solution in terms of molality with respect to the provided solute, right? So molality is equal to moles of solute NB by mass of solvent in kilogram. WA is for solvent, B for solute. So WA is the mass of solvent in kilogram. So now you can simplify this. Mass of B by molar mass of B into mass of A if it is represented in grams. So here you have to multiply with 1000. So this is the molality. What is the unit for this? The unit for this is moles per kilogram, right? See, what is the relation between this normality and molarity? So you can write a relation between molarity and molality. Molality is equal to 1000 into m. Capital M is the molarity divided by 1000 D minus M into MB. So this is the relation between molarity and molality. Molality and molarity. What are the different terms which are used here? See, small m is the molality, capital M is the molarity, MB is the molar mass of solute, and D is the density of solution in grams per ml. Unit is very important, grams per ml. So from this formula you can relate directly molarity and molality, right? And one more relation we can write here, relation between molality and mole fraction. Relation between molality and mole fraction. Right? So see, molality is equal to, you have relation moles of solute by mass of solvent in grams. So here multiply 1000. So mass of solvent, you can replace this moles of solute by moles of solvent into molar mass of solvent. Wa is equal to Na into Ma, you can very easily write. Now Nb by Na, you can write mole fraction of B by mole fraction of A into Ma into 1000. So this is the mole fraction of B, and this is the mole fraction of A, and this is the molality of the solution. Ma is always constant, so you can very easily calculate the mole fraction if molality is given, or if molality is given, then you can calculate the mole fraction, and similarly if mole fraction is given, then you can calculate the molality, right? So from this you can calculate the mole fraction as well as molality, or vice versa. So this is a relation between molality and mole fraction. Now you can see molality mole fraction, mass fraction, all are temperature independent. All are temperature independent. Why they are temperature independent? Because no volume term is there. In all these cases you have mass relation, and you know moles is also related to the mass directly, so they are independent of temperature. But remember one thing, whatsoever first I have to complete, and molarity, normality, they are temperature dependent. Because they have volume, and you know T is directly proportional to V. So on changing temperature, volume will increase. So accordingly, normality, molarity will decrease. But remember one thing by this word, this generalization is applicable only at room temperature, near to room temperature or above the room temperature, but not valid at lower temperatures. At lower temperatures, all the above whatsoever I have written here, all are temperature dependent. So if solvent, so we can say temperature, this is very important note you can make. This is very important note that temperature below the melting point or freezing point of solvent. Temperature, or you can say any temperature below the freezing point of solvent, all concentration terms are temperature dependent, right? Below the freezing point of solvent, all concentration terms are the temperature dependent. Again, the question arises how? See, when you freeze any solution, solvent will freeze out, and once the solvent will freeze out, that the freezed part of the solvent will constitute the heterogeneous part of the system, heterogeneous part of the solution. For example, you take aqueous solution. So when you lower the temperature of aqueous solution, water will freeze below 0 degrees Celsius and it will appear as ice, because you know freezing is always takes place for pure substances. It is not, although there is some impurity may be there, but it is assumed that if an aqueous solution is freezed, water will separate, ice will separate out and other component will separate out. Means if you have freezed the H2SO4 aqueous solution of H2SO4, then ice will separate out and H2SO4 will separate it, right? So what will happen when you decrease the temperature of an aqueous solution below 0 degrees Celsius? What will happen? Ice will separate out, and so whatever amount is separated out at that temperature, because you know, suppose that you have decreased the temperature -5 degrees Celsius, so at -5 degrees Celsius, whole water will not freeze. Whatever amount of water is freezed at that temperature, that will constitute the heterogeneous part of the system, and if it is part of the heterogeneous system, then it will be not included in the what concentration. So in that situation, you have to remove that quantity from the solvent and from the mixture. So in this case, all these terms, whether they have volume relation or not, they are also depends on the temperature. So molality, remember this point, molality is also temperature dependent, but below 0 degrees Celsius for aqueous solution and below freezing point of any solvent. So don't be confused, because once you are decreasing the temperature of solution, solvent will freeze out, and if solvent will freeze out, then concentration will change irrespective of the involvement of volume. So this generalization is true only above the freezing point of solvent. Okay, so hopefully all of you are clear regarding this, right?